Welcome to Making Stuff with Chris DeHut. I'm Chris. At least last time I checked I was. In this video we're going to be talking about LEDs. These wonderful little communicating devices that are found in just about everything that's electronic today. What we're going to be covering today about LEDs will be what they are, a very brief history about them. Then we're going to go into some coding about how to turn them on and off, very simply, for blinking. Then we're going to control the brightness of it using PWM, create a fade on and a fade off effect with another little program, and then finally another program that will be used to demonstrate how you can communicate with a single LED a secret code. And that'll be our last example for this video. We'll get started with a brief history of the LED. The earliest reference I can find to a light-emitting diode goes back to 1927. Now, at that time, it was more theoretical than practical because there would have been no application for them at that time, or practical application. Throughout the 1960s, the manufacturing process was refined so that they could be implemented both cost-effectively and with a useful lifespan and so forth. Furthermore, the light-emitting diode was given color during that time frame. Now, in practical use and applications, that really began in the early 1970s. And if you grew up in the 70s or lived through the 70s, you'll know what I mean. It seemed like they could put an LED on everything. Now, here we are, a half a century later, give or take, and the LEDs are still commonly found on all sorts of devices. So I think there's a very bright future yet for LEDs. Pun intended, of course. Now we'll turn our attention over here to my inventory of LEDs that I keep right here on my electronic bench. As you can see, they come in a variety of colors. We've got red, green, yellow and amber, white, blue, and then clear lens blue. And then this looks like it's yellow, but these are high-powered white LEDs. These are literally 1-watt LEDs, very, very bright. I use this style in a lot of devices where I want to add illumination. And then a few surface mounts. I have a slight difficulty working with the small ones, so I don't keep a lot of the surface mount LEDs, but they come in the same colors and varieties. These are the two most common sizes that you'll see utilized today. This one over here is what's considered a 5 millimeter, or in the inch world we would call that 200 thousandths in diameter, and this one's a 3 millimeter, or about an 1/8 inch in diameter. And these are two very common sizes that are used frequently. Now, as I briefly alluded to, this is a very high-powered LED, and that is used primarily for illumination. This style of LED would be found in light bulb replacements that we're seeing used throughout everywhere today, from residential lighting, industrial lighting, lighting on highways. Stop-and-go lights are using these high-powered LEDs to replace the old incandescent lights. The primary driving reason, they're very efficient at converting electricity to light without wasting a lot in heat. Now, the one thing that almost all LEDs have in common when we see them on electronic devices is they're great communicators. For example, we might use a red LED to alert us of a problem, or maybe power is on. Green could be communicating to us that all systems are good and go and functional, no worries. Yellow could easily communicate a pending problem or a certain issue that needs attention. Often clear ones are used as illumination, perhaps not in the sense of communicating anything by color, but still it's helping us. Blue could indicate a certain status of something on a device. Further to communication in a very refined method, everybody's got a remote control. I've got one there, one here for one of my cameras, a few more out of reach. We use them for a wide variety of devices, and when paired with an infrared receiver, which I'll show you if I get this package open, this device would be the receiver. This device is an infrared transmitter, infrared LED. It's transmitting. So it's going to send a code to this device. This device will read it and perform some action. And that's what's going on with all the remotes that you're using in your house to communicate with different devices. So in the world of communications, LEDs are really king of the road right now and have been for a very long time. We use them to communicate the simple things, as I just mentioned. I will be talking about using a single color LED to communicate a code, which you'll see used oftentimes for diagnostic communications from a device that doesn't have an LED display or LCD or a monitor display. They will use a single LED, single color LED, and pulse it in a certain sequence to communicate a message. And another aspect of LEDs that is becoming common is using them in lighting effects, where we want to maybe mix colors with a red, green, blue LED, which is the subject of another video that I'll be producing. But you mix colors or fade them on and off to create an ambiance or an environment that's pleasing and so forth. So all around, LEDs are just tremendous little communication devices that also serve extremely good at illumination. Now, to utilize an LED, we have to provide power and current to it. Power in the form of voltage, current in the form of milliamps on these very small LEDs. And the way to figure out which way to wire them, I'll give you a few pointers here. The anode, which is the positive side, is the long leg. And you always think of it this way. Long legs are a positive thing. So that would tell me right there that I know to put my positive lead on the long leg. An LED of this style will also have one side flat on this little flange area here. And that will be connected to the short leg. So obviously that would be our ground or our 0 volt side. Now we can't just hook up voltage like so. Now at this point I don't have my power supply turned on, but if I were to put anything other than the forward voltage of the LED on here, it's going to blow. And let's take a look at what that looks like when it happens. So I'm going to turn up my voltage very slowly until we see the LED come on. Okay, right there the LED is on and I'm at 2.5 volts. And I'm going to continue to increase voltage and it'll get brighter and brighter. And what we're going to see is at some point I'm at 3.5 volts. It's going to get so bright, 5 volts. I'm up at 7 volts. Uh-oh. It just died. And at that point, it's actually pretty warm, but it's dead. Now, sometimes if you lower the voltage, there's still a little life in them, and this one is completely fried. So we need to be able to deal with that. And what we're going to do, let's take a look at a data sheet so you can figure out how we can work with an LED at different voltages other than its forward voltage without it hurting itself. By no stretch of the imagination do I consider myself an expert when it comes to reading and interpreting data sheets for electronic devices. But luckily, LEDs are pretty straightforward, and I can walk you through with some confidence to help you find the data that you're looking for. Now, we'll look at a couple different data sheets from different manufacturers so you get a little idea how to hunt for the data. First thing you'll want to do is figure out or find the data sheet for the color LED that you have. Now in this case we'll be comparing two different red ones and then we'll look at a blue one. But here we're on a red LED and what we're going to look for is this is the first thing I want to talk about, absolute maximum ratings. Now, a lot of people think, oh, gee, that must be what I can work with. No, that's the absolute maximum ratings. So you exceed this, and then the magic smoke comes out of the LED and it doesn't work anymore. But it does give us a guide point or a limit as to what we can do. And the first thing that we want to see out of this is if you can see a continuous forward current, maximum 20 milliamps. That's a real key indicator. So that's going to tell me if this is the maximum, we want a forward current less than that. Further down, what we would hope to find is forward voltage. The other one was forward current, but this one is really the more important one to begin with. Forward voltage, often abbreviated VF. Here they're showing typical maximum. Well, we don't want to go to maximum, but typical is really where we want to target all of our measurements at. And at forward voltage of 2 volts, we would get 20 milliamps. And if we remember earlier, that was the maximum that we would want up here. Continuous forward current, 20 milliamps, being, again, a little further up, absolute maximum. So we need to derate everything so that we don't get up to 20 milliamps. But we're going to need this number to calculate that. And we'll discuss that in a minute. Another item that you really want to look at are the graphs. They tell a bigger story. Here we're looking at the forward voltage going through the LED or when it turns on. And this kind of tells us our forward current at that forward voltage. And right in this area is about where we want to be. Unfortunately, this chart really doesn't tell me enough, and at least not very simply and clearly. And then here it's going to tell us our forward current with the luminous intensity. Again, it's information, and depending on how much of an engineer you are, you can garner something useful out of this. Now let's look at another one, another data sheet. This one is, I think, from a German company. Reading that, I would have to say that's probably German. But here we're going to look again, absolute maximum ratings. Remember, we don't want to use that as our setting. Peak forward current is 100 milliamps, so that we can give it a real peak momentary forward current at 100 milliamps, and it might survive. Continuous forward current is 30 milliamps, so it can actually handle quite a bit of power going into it, 30 milliamps as maximum power. But again, that's not telling us enough information from which to make our calculations. Here we're going to look at our forward voltage to get what they considered their test conditions of 20 milliamps. Their forward voltage was 2.1 volts. Here's your indicator of what this value means, V. So at 2.1 volts, we can achieve 20 milliamps of current, and that ran on their test data. Now, the more important part is this chart right here, which I just love. Here's our forward voltage, the voltage at which the LED turns on. And we see where the line is solid, which think of that as telling us that that's okay. And then anything above 30 milliamps, it's up to you. It may just go put, 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 and die out with the magic smoke leaking out of the LED. A rule of thumb is you want to stick under that maximum forward current, of course, and you can target somewhere in the middle. So in this case, I would say, well, if I go with 15 milliamps of current going in it, that's about the middle of the safe zone. And of course, if you want it brighter, you can work your way a little closer up. Or if you want longevity of the LED, you can come down a little bit further. Depends on what you want to do. Now for the red LEDs, we saw that the forward current, or the forward voltage, where the LED starts turning on at, is 2 to 2.1 volts. Now for blue, what we're looking for in this data sheet, somewhere right here is telling us it's a blue, and it's a water clear lens. What I want to do is see my forward voltage. Notice on blue, that forward voltage is 3.3 volts. And at that voltage, we would have 20 milliamps of current. And that's the key element for figuring out what resistor we need to limit the current that we're putting into the LED. Not all LEDs have the same forward voltage. So that is why we have to look at the data sheet rather than just guess. Now, over the years, many tinkers in electronics have come up with a very simple rule. And that is, if I use a resistor of somewhere between 220 and 330 ohms, I'm going to probably be okay, and the LED will be a little on the dim side. And in truth, that will work for 5 volt electronics and 3.3 volt electronics. I just wanted to take you through this process a little more engineering-like so that you know what you really should be doing. So hopefully you can find forward voltage and your forward current that's not at the absolute maximum, wherever that is on this particular data sheet. Oh, here it is. Here's our absolute ratings. You know, don't work in this area, that 30 max milliamps. Pick a number lower. So again, half of that from off to on would be about 15 milliamps. Target that, and you can go up or down a little bit. So now let's see how to take these numbers and do something with them so that we can calculate a resistor. Now let's turn our attention to calculating the resistor value to limit the current to what we found in the data sheets. Now the formula is our resistor in ohms, our resistance in ohms, is equal to the supply voltage minus the forward voltage of the LED divided by the forward current of the LED. And of course, that's the desired amount. So first we'll take a look at an example for what would work on a typical red LED. Now again, the supply voltage we get from the Pico is 3.3 volts. An Arduino might be 5 volts. Other microcontrollers can be of any voltage. So you need to understand that part first. Our forward voltage, we find that in the data sheet. It's expressed in volts. Our forward current we get from the data sheet, and that's expressed in milliamps. Now, for the red LED example, it would have been 3.3 volts minus 2.1 volts of forward voltage of the LED. Divide that by the milliamps. 0.01 is 10 milliamps, and that would equal 120 ohms. So you would have let me grab a 120 ohm resistor, and I'll try to get that in front of the camera here. And that would be your 120 ohm resistor. And the colors are brown, red, brown. Now for blue LEDs, the forward voltage is 3.3 volts. Interestingly, that's also our supply voltage. So how do we work that? Because if I take 3.3 minus 3.3, we end up with 0, and that divided by 0.015 isn't going to give you a useful value. So how do we deal with that? Well, technically, as I'll show you over here on the bench, we've got my power supply is set at 3.38 or 9 volts, and you can see that the current being output is 30 milliamps. We go down to my test circuit, and you'll see I've got the positive lead going into the long leg of the LED, ground going to the ground side of the LED, and it's running at a very comfortable temperature. It's not hot. That's because the forward voltage matches the supply voltage. It's when our supply and forward voltages don't match up where we've got to limit the current. In this circuit, everything is, we'll call it self-regulating. However, that's not what I recommend even for a blue LED. Now back here on the bench, I'm going to take my red clip off and I'm going to put it on the far side of a 120 ohm resistor. And you'll notice that the LED still lights, it's still bright, but at least there's some current limitation going into that LED. And it's better to put on a very low resistance LED, or I'm sorry, a very low resistance resistor, just to give the LED some protection. So that's what's going on, and I would always recommend that. Now when we get over to our test circuit with the PICO, we're going to be working with a red LED and a 120 ohm resistor to limit that current. Now as a reminder, I would like to point out that earlier for reference material we were looking at data sheets from various manufacturers of LEDs. For working with the Raspberry Pi Pico, one of my favorite resources is the Getting Started with MicroPython on the Raspberry Pi Pico. And you can download that or purchase it off of the raspberrypi.org website. Now before we get into the code examples, let's take a look at the circuit in a fritzing diagram. We've got our Pico here. This is a ground pin, pin 38. It's ground. We take that to the ground rail, where I've got my resistor, which is a 120 ohm resistor, and that goes to, in this case, the negative side of my LED. On the positive side of the LED, I've got my wire coming from pin number 4, which is GP pin number 2. So that's our 3.3 volts. When we turn that signal on, goes through the LED, through the resistor, and then back to the ground input. Now the resistor could be on either side of the circuit. It really doesn't matter. I just draw it this way because it fits nicely on the breadboard. Now let's start taking a look at working specifically with the Pico in MicroPython. Now for our first example program, we're just going to have a very simple program that will blink the LED. It starts out, we're going to import a couple of libraries. Machine, which is a library for MicroPython to allow it to work specifically with certain microcontrollers. In our case, we're working with the Raspberry Pi Pico. Then we're going to import UTime or MicroTime as a library to help us with creating like a sleep for our loop cycle down here and other timing operations if we needed them. So the first thing we're going to do is instantiate this class of an LED. In our case, we're using the pin as an LED. So we do that, LED equals machine.pin. Then I'm using GP number 2 right there. And then machine.pin, and I'm setting it up as an output. Then I just have my ready, set, go before we enter a while true loop, meaning a continuous loop that never ends. And then to turn the LED on, I'm going to turn on the LED by setting its value to 1. 1 is generally considered on. We'll sleep for 1 second, then we will set the value to 0 for off, and then we'll sleep for a 1/4 second. Very, very simply. So literally, this creates an object that we can control for that output pin that is attached to the LED, and we could have called that anything. And this is how we turn it on and off, the LED.value. Let's run it. Got to clear that out and reset that. Okay, now it's happy, and we'll go ahead and run it. And here it is running. Unfortunately, it's hard for the camera to pick it up the way we see it as a human, but you can easily see it going on and off as described. Quite simple. And of course, you could leave it on or you could leave it off. It's up to you what you're trying to communicate with that LED. For our next example, we're going to fade on and fade off the LED. That's a cool lighting technique that you'll see on a lot of electronic gizmos these days to make it look more cool. But nonetheless, it's very fun to do. Now it's going to use pulse width modulation. And I've got another video that'll go into that in great detail. So I'm not going to cover it in a lot of detail here, just going over the basic instantiation of it as well as setting the duty cycle. But just as it was with our last program, we're going to import our libraries. We will create an object by instantiating it, the pin function here. And we're using PWM, pulse width modulation, and we're going to assign that on machine.pin number 2, same GP number 2 we've been using. And we'll give that a frequency of 1,000. For now, just consider that a good value. And then I'm going to set up a loop here, and I want it to not go real fast and not go real slow. Now here we're going to set up a fade rate that helps slow down the process of fading on and fading off. It's just a delay within our loop. And this will be the variable that's going to hold that as part of our PWM signal. I do my ready, set, go, and then we enter our loop. V is holding the PWM signal, the duty cycle, and we're going to increment that by 3. And that'll count all the way up to the maximum allowable or 100% duty cycle up here. And that's when it'll break out of that loop. We will set the LED's duty cycle of the PWM, and that then sleep for a very brief period of time. Up here our fade rate, just so that we can slow things down. Print full on, we'll see that down here. Sleep for a little bit, and then we'll reverse the process down here by decrementing our PWM's duty cycle. So let's watch that run. And you can see that going bright, dim, bright, dim, bright, dim. Very cool, very simple, and of course you can do that any which way you want on an LED to get the effect you're looking for. Now we just saw how to fade an LED on and off, and that's a cool effect, but maybe you're building your electronic gizmo and you want the LED to be at a specific brightness. Now using the resistor of 120 ohms in this example, that gave us a good, comfortable brightness range with a safe current rating. But maybe you want it to be half as bright. You could change out the resistor, or as programmers, we'll change it through PWM's duty cycle. So looking at the program, this is very close to what we had the last time. Import our machines, instantiate our LED object, setting up it as PWM output, pin number 2, we'll set the frequency to 1,000, we'll run the thing. We'll set our max duty to 65,535, which is the maximum we can put for the frequency, or I'm sorry, the duty cycle. And then what we will do is we will set it here at 0% or 0 times the max duty, 25 times the max duty, 50, 75, and 100%. So this will just run continuously because it's in a continuous loop, but it shows you what each of the different brightness levels will be. So I'll get this so you can hopefully see it. I know it's kind of hard on the camera to pick that up, or you're seeing it get brighter, 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 and then off. So this is a way for you to control brightness of the LED with software as opposed to changing out a resistor. And of course you could put just one of these sections of the code somewhere in your program to control that brightness. You don't have to do this through a loop. Now for our last example, I created a function in this little example program that allows you to communicate in a very simple code. But if you've ever done diagnostics of certain kitchen appliances, industrial equipment, many devices that just have a single LED for communicating something to you, this is the process that they use. Now the first thing we'll do, we'll run it. I'm going to show you what the code looks like that we're going to communicate. We will have the first group of codes will be long, short, long, short. And that's the on time for the blinks. Then we'll go on to the next message, and that will be 4 long on blinks. So long, 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 long. And let's just see what that's going to look like to start with. There was our clear. Long, short, long, short. It'll be a blink 3 times. Next message, long, 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 long. Pretty straightforward, right? Now, of course, there would be some meaning applied to that blink sequence, and you'd have to provide that in your diagnostic information. But with just 4 blinks, you can communicate a good number of different messages. So let's look at that in code. I did it in a function. We're going to, the message will consist of 4 characters that are either of the letters S or L, short, long. The total duration for a single character is 2 seconds, so the whole message of 4 characters is 8. A short blink is on for 1/4 of a second and then off for 1 3/4 seconds. A long blink is on for 3/4 of a second and off for 1 1/4 seconds. And of course, this is all just numbers and timing that I picked based on roughly what the last thing I diagnosed like this. That seemed to be about what the durations were. You can modify it to suit your needs. Now, when this function is called, the first thing it's going to do is go through and turn the LED on and off rapidly. And that kind of sets up the start of a new message. And we saw that blink very rapidly. Then we come down in here, just do a little error checking. But now we're going to take the message that was provided to it via this variable right here. For each character in the message, the character will either be a long or a short. Here we're going to turn for a long. We're going to turn the LED value on, turn it on, sleep for our long delay, turn it off, sleep for our 2 seconds minus the long delay. Remember, we're working from a 2-second constant for each character. And then we would sleep for our off delay. So it goes back and forth through our longs and our shorts. Same thing down here, but instead of long delays, we're sleeping our short delay times. And that's the whole magic of it. And you will see this technique used in instruments and devices of all values and types. I've seen them used in cars, industrial machinery, kitchen appliances, furnaces. You name it, you will see a blink sequence like this communicating very effectively what is wrong, and it's trying to communicate that to you. So we'll watch that one more time. There was the blink, long, short, long, short, clear message, long, 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 and long. And that was sent to the function by saying coded message, and then giving it the sequence of the letters, 4 letters, L, S, L, S. But that's it, a very simple technique to communicate a code from the device. That could be diagnostics information or some form of information to get back to the end user. And of course, it can be implemented very inexpensively. Typical LED today is a couple of pennies. A typical resistor today is a couple of pennies. So the device is incredibly inexpensive. And as far as the Raspberry Pi Pico goes, you do have a limited number of pins that you can use for various purposes. So it's very economical on the usage of pins. We're using 1 pin to communicate a variety of messages. Now, this is pretty well going to wrap up our discussion on the basic single LED. Unfortunately, as I usually do, I got long and lengthy, but for a beginner, I think there's some very good information in there. As mentioned, I have other videos. One in particular that you should probably reference and watch is on the Raspberry Pi Pico using pulse width modulation, or PWM. And then you can learn more about the PWM signal and its many other uses as well. So that's going to wrap it up for this issue or this video. I really appreciate you taking the time and spending it with me today on this project, and hopefully you liked it, and if so, I sure would appreciate it if you would subscribe. Looking forward to seeing you in the next video. I'm Chris DeHut for Making Stuff with Chris DeHut. See you next time.